Hello everyone, and welcome back to another geostatistics lecture video. And in this lecture video, I want to go through how we actually calculate the Ripley's K function. This is going to be the most simple calculation. There are other versions out there that are implemented in modern software packages that account for a variety of different edge effects and different things. But in terms of understanding the concepts of what Ripley's K is doing, starting off with the generic function works just fine. So let's go ahead and talk about what we're calculating, right? So we're calculating Ripley's K. So the way this works is we are going to, again, going back to that idea, the first thing we want to do is we want to calculate all the distances. Then we want to pick some threshold, and then we want to compare the threshold to the distances. And in our nearest neighbor example, right, we did the summation, and then we had this symbol like that, and in there we had di comma d, or in this case we used r because r was the radius, right? What we're doing in this case, let me erase that so we don't confuse ourselves. We're going to do something very similar. But now, right, instead of doing just the point to its nearest neighbor, what we have to do now is we have to consider the distances between all points. And that's going to look a little more complicated, but I promise you that it's not really. Instead, we're going to do double sum of I to m and j to m. Now this double loop, this double summation, this is going to make sure that we get every single distance. Right? And we're going to have the same sort of weird symbol here. And it's going to have d, but in this case it's going to be ij, because it's going to be the distance between the ith point and the jth point, not just the distance to the nearest neighbor of I. And then we're going to pass in that r again. Right? So just to sort of make sure that we let me move up just a little bit, to make sure that we sort of understand, again, what this is doing is this is saying that, if dij, right, if the distance between the ith point and the jth point is less than r, right, it's supposed to be an r, not a p, is less than r, right, this is going to be 1. We're going to keep it, right? It's 0 otherwise. Right, so this is a fancy way of only keeping those distances, right, counting up those distances that are within that radius. So this is very similar to what we saw before. Now here's where it gets tricky. We're going to be multiplying it by a constant. And that constant is going to be the area that we're looking at over the square number of points. And this is the Ripley's K function, right? It's pretty straightforward in terms of the equation. It looks daunting, but it's really not that bad. So how do we interpret, right? How do we interpret the K that we get, right? Assuming A and M are consistent, right? Assuming that we're not changing A and M, because again, changing A and M is going to change this whole picture, right? But assuming that these two things stay the same, right? Your higher Ripley's K's, right, mean more points are closer together. And this is going to indicate potential clustering. Right. Your lower values mean points are farther apart. All right, and this is going to indicate potential dispersion. Right. So again, we're assuming that these two things aren't changing. And that would make sense, right? Because this is going to be going on the numerator, right? When you do all this math, right, this whole summed thing is going to go on the numerator. So the more points that are within that radius, right, the larger the numerator is going to be, the larger the whole number is going to be. So again, the higher this number goes, relative, assuming these don't change, right, that means you're having more points that are closer together. And this is going to potentially indicate clustering. And again, potential is really important here, because as we're going to talk about in the next video, right, we're going to talk about what is this relative to, right? This has to be relative to something for us to be able to make a meaningful comparison. But again, right, assuming the A and the M stay the same, generally higher K means points are closer together, lower K means points are farther apart. Hopefully this makes sense. And as always, please reach out. Thank you.